So since negative feedback seems to be playing a crucial role here, let's actually take some time to understand negative feedback in some detail, and then we'll continue the discussion with OTAs. So firstly, this is your classic negative feedback. I'm sure you have seen this 9,99,999 times. This is the 10th lakh time you are seeing, let's say. So what is the closed loop transfer function from Vi to Vout here? A by 1 plus A beta, fine. This is, let us say, Vout by Vout. And by the way, how do you determine if this is negative feedback or positive feedback? Yeah, break the loop and okay, and
check whether it's got the same direction, outputs are in the same direction or opposite.
Yeah. So the idea is, remember, the main reason to use negative feedback is this. See, if let us say the gain A is really large, what can you say about this voltage, this signal? If this gain A is infinite, what can you say about this signal? This should be 0. Same thing. So infinite gain times 0. So which means, what can you say about the input signal and the feedback signal? They have to be equal. So which means my Vi must be equal to Vout by beta, right? So remember, the main reason for using negative feedback is to make sure that you get an accurately controlled output quantity, right? As long as your gain A is really large, you know this is approximately 1 by beta. It doesn't matter if my gain A is changes from a million to 2 million. My closed loop gain is going to be almost same, 1 by beta. So main motivation is to make sure that we are able to get something at the output which is precisely controlled. So which means, if we are having a case where the output is precisely controlled, anytime there is a change in the loop for some reason. So let us say, for example, my Vout increases for some reason. Now I want to make sure my Vout doesn't change, so that it is accurately set. So if at all by mistake Vout changes, how should the loop act? Should it further increase Vout or reduce Vout? That's how you check it, whether it's negative or positive feedback. Again, for checking it, you typically try to break this feedback loop. Any question? Oh, sorry. Yeah, again, see, it's a test to check if everyone is paying attention. So, yeah, thanks. Yeah, to check if it is in what kind of feedback loop our loop is, you basically break the loop somewhere. This is an ideal block diagram. You can break the loop anywhere. So let us say you break the loop here. Assume that some signal here is increasing or decreasing, doesn't matter. So you trace around the loop. If the loop is negative feedback, so what should happen here? Should the signal here increase or reduce? It should counter it. So let's check it. If this increases, what can you say about this signal here? So which means, what can you say about this signal? So if this signal increases, what can you say about this signal? That will decrease because you're subtracting, so which means this is a negative feedback. Great. So now tell me, I'll show some circuit. Tell me if it's a negative feedback or positive feedback. So do you think this is a negative feedback or positive feedback? Negative feedback. So we can check it. So how do you check it now? What do I do first? I break the loop somewhere. Again, let's say I break it here. Oops, sorry. And then what do? I make some change in the loop. So let us say I increase the voltage here. So what will happen to the output voltage here? That will decrease because you are increasing the inverting terminal. So if this voltage decreases, what can you say about this voltage? That will also, of course, for this you can assume that input to be 0, doesn't matter. So which means this is basically a negative feedback loop. Okay, so now tell me this. I'll do this into it again. So let's say now we have something like this. So do you think this is now in negative feedback or positive feedback? Negative feedback? Why? Yeah, again let's check it. So once again, let us say this time I try to reduce the voltage here. So if I reduce this voltage, what will happen to this voltage? So what will happen to this voltage here? That will decrease. So which means what will happen to this voltage? So the loop is not countering the change I made, so this is in positive. So again, this is a common point of confusion. Just because the output signal is fed back to the inverting terminal of the op-amp doesn't necessarily mean that we are having a negative feedback loop. Right? So now tell me, let's say I give something like this. Let us say now I have two op-amps, in my circuit. So let me call this A, B, C, D. So again, our job is to make sure that if I have 10 op-amps in my circuit, all the 10 op-amps should have DC negative feedback, correct? So tell me then, how will you find out the signs of the op-amp here? That is, how will you find whether C is positive or negative, so that all of them are in negative feedback. And again, remember, our goal is to make sure both the op-amps, let us say this is op-amp 1, op-amp 2, both of them should be negative feedback finally, right? So how do you think we can go about finding what are the correct signs? We can? Yeah, I mean, you can, because there is only two possibilities for C, plus or minus. You can assume something. So what do you want me to assume? So let us say I'll assume plus, minus. So again, I need to check if the assumed sign is correct or not. What will I do? I have to break the loop. So let us say I break the loop here. Right? And let us say I go and increase, let us say, this voltage here. What will happen to this voltage? So if this voltage increases, what might happen to this voltage? So which means what should be the correct signs now? What I assumed is incorrect, so which means I have to flip it. So the correct sign is going to be, this is minus and this is plus. Okay. So that sets the correct signs for op-amp 2. So let's look at this fellow. So again, we can assume that, let us say I'll assume again this is plus and minus. So we can check if the assumed signs here are correct. So once again I'll break the loop. Let us say increase the voltage here. What will happen to this voltage? That will increase. So if this voltage increases, what can you say about this voltage? Increase or decrease? I mean, this is basically an inverting amplifier. So this voltage will decrease. So if this decreases, what can you say about this voltage? So is the assumed signs correct or incorrect? So which means for the first op-amp, this is the plus terminal, this is the minus terminal. Again, you notice that, I mean, although the feedback seems to be going to the non-inverting terminal, this is the correct way for the op-amp to be negative feedback. Right? So it is not always that the feedback should go to the inverting terminal. That is completely incorrect understanding of negative feedback. Okay, so I'll give you one more. Let me take So A, B, C, D. Tell me what should be the correct signs for C and D. I mean, okay, tell me what should be the positive terminal here, C or D? C. Why? Okay, so again we can assume something, right? So let's assume that C is negative, this is positive. That is the assumption I'm making. So I have to check if the assumption is correct or incorrect. How do I do now? I break the loop somewhere. So let us say I break the loop here. Okay. So once again, let us say I increase the voltage here. What will happen to the output voltage? That will increase. So which means if this voltage increases, what can you say about this voltage? That will also. So which means the assumption I made is incorrect. So which means I have to flip the signs. So that will fix this fellow. Similarly, you can do for the first op-amp. So can you work out and tell me what is the correct sign for the first op-amp? So positive, I want A or B. B is negative or positive? I mean, you are saying positive is B. So this is the signs. So you can work out and check. This is what you should do. Okay. So let me show you one more example. So let us say, doesn't matter. Let's say I have an input current here. So here, how will you find what is the correct sign? So looks like I have feedback to both the terminals of the op-amp. So which means, do I only have negative feedback or do I only have positive feedback? You actually have both. Whatever you assume, you're going to have both. But finally, what should dominate for op-amp? At DC, at least we should make sure that the negative feedback dominates. So how do you check what is the correct sign now? You apply voltage at VA and VB. Okay, and I mean, remember, we are looking at, it is known that now we have both positive and negative feedback. Our goal is to make sure that we assume an appropriate sign so that the DC negative feedback dominates, right? So again, remember, for checking the signs, we can assume the inputs to be 0. So I'll assume the current to be 0. So this is open circuit basically. So once again, now I have to break the loop somewhere, right? So where do you think I can break the loop so that both the loops are broken? I'll basically break it at where? At the output, right? If I break at the output, at least both the loops are broken, so I can see which is basically stronger. So now let us say there is a change here. Let us say it increases by some delta V, increases by plus delta V. How much will be the change that will be reflected here? The entire delta V will drop here, because it's an open circuit here. So how much of delta V will drop here? Delta V by 2. if the overall feedback should be negative, now if I increase this voltage, what should happen to this voltage? It should decrease. So what should be the correct signs for A and B so that the output voltage decreases? What should be negative? A should be. So which means the only possibility is for me to have A to be. So the correct assumption is, the correct sign is A should be negative and B should be positive. So in practice, we can also have something like this where you can have both positive and negative feedback. You kind of make sure that at DC the negative feedback dominates. Is it clear? Great. So now that we know some things about negative feedback, so let's move on, continue our discussion. So as we saw, if I have my single stage OTA, so it is a first order system, approximately at least a first order system. If I have multi-stage OTA, will it be a first order system? Yes or no? No. So it's going to be a higher order system. So I'll say order greater than 1. And I know I'm going to use the OTS in negative feedback. So let's actually see what will happen if I use a single stage OTA negative feedback. Similarly, I'll see what will happen if I use a multi-stage OTA negative feedback. That's the next step to do. So let's just briefly look at single stage today and we'll wrap up. So again, a single stage OTA, remember I can approximate as a first order system. So I'll assume that my transfer function is some A naught by 1 plus S by P1. Now let's say I put this in negative feedback. So this is now A of S. This Vi V out. So this is the A of S here. Right? Now remember, anytime I put some system in negative feedback, what is something that can go wrong? If a system is put in negative feedback, what is something that can go wrong? The system can become unstable, right? It is possible. So let us actually see what's going to happen here. So here, this is the A of S. So can you tell me the closed loop transfer function in terms of A of S? In terms of A of S, can you tell me what is the closed loop transfer function from Vi to Vout? A of S by 1 plus beta times A of S. Same thing. Now you can substitute the value for A of S here and can do the calculation. It will come out like this. So A naught by 1 plus beta A naught times 1 by 1 plus S by something like this is what. You can do the calculation, but this is what you get. So tell me now, this is the closed loop transfer function I get if I put my first order system in negative feedback, right? So if I tell you that this is the closed loop transfer function I get, tell me if this system is stable or unstable. Or how can you tell if a system is stable or unstable? Pole should be where? In the left half of? So do you think the pole here is in the left half of S plane? Yes? Why? Because A naught and beta are positive. So where is the pole located here? So let me just remark it here. The closed loop pole, where is it located? What is the location of the closed loop pole? Yeah, let's say it's in LHP. I will not show the negative sign. What is the location? This is the transfer function. Where is the pole location? Okay, minus what? 1 plus beta a naught. Again, for very large values of a naught, you can approximate as beta times a naught times p1. So again, this system is stable or unstable? So do you think it can become unstable? No? Yes? Sometimes? I mean, assume that you have put in negative feedback, right? So if you design for any value of a naught, any value of beta, you think this can become unstable? No, right? So which means a first order system, if you put in negative feedback, it is guaranteed to be stable, right? So that is something to have in mind. I'll say first order system in negative feedback is guaranteed to be stable. So one more thing. So here I can write the closed loop transfer function in a different way. So I'll write it as 1 by beta times beta a of s by 1 plus beta times a of s. And what is this beta a of s called as? It's not open loop gain. Okay. So let us say you have, this is the negative feedback loop. So this is the negative feedback loop, right? So let us say you break the loop somewhere by de-energizing the input. So let me erase this. So let us say you make the input 0 and break the loop somewhere. To check if it is a negative or positive feedback, what do you do? You break the loop. So let us say you break it here. And then what do you check? And then what do you do? Yeah, let us say you increase some voltage. So let us say there is some test voltage applied. So how much of this will come back here? What will be the signal that returns back? Can you check carefully? Minus? Okay. Yeah, sorry, into Vt. So this ratio, I will say negative of the return voltage to the applied test voltage is what we define as the loop gain, because that is the gain you have when you actually go around the loop completely. So we denote it as Lg. So which means my closed loop gain I can rewrite like this. H of s is 1 by beta times the loop gain by 1 plus loop gain. And now let me just do one last remark. So here if I try to sketch the loop gain, so let us say this is my loop gain. Loop gain is, in this particular example, my loop gain is basically equal to beta times a of s, right? So my loop gain is beta times a of s. So this is beta times a naught by 1 plus s by p1. Let me also remove this. So you can take it as an exercise and please work out what is the frequency at which the magnitude of the loop gain becomes unity, right? I'll say find the magnitude value of omega at which the magnitude of the loop gain becomes 1. And this is a reasonably important metric, because remember, if you have a loop gain much greater than 1, you have a strong feedback. If the loop gain is less than 1, there is basically feedback is not active. So this frequency acts as a pointer or a metric to say whether my feedback is strong or weak, right? So that's why this is something to note. So you can calculate and come in the next class. So we'll continue from that in next class.